Good. So, hi everyone, welcome to the GOCC. We're happy to have Sophia Garzon Mora speaking today. And before we get started, I just want to remind us of our community agreement. In short, we're all learning. Everyone has something to contribute, and no one has all the answers. And with that, take it away, Sophia.
Thank you. So I'm really happy to be here, but maybe so I like giving talks where people actually interact, but this is kind of hard via online talks. So I'm gonna just ask random questions at some point, and maybe someone will answer. Otherwise, I'll just answer myself, and we'll see. So yeah, maybe my first question to you is, how familiar are you with Ehrhart theory? Like, have you heard about this? Is it completely new? No, okay. So I'm nodding.
Very lightly.
Very lightly. Okay. No, that's perfect, because then let me start by giving a brief introduction on Ehrhart theory. So what we want to do now is, the idea is we want to count points in polytopes. And so we're going to do some examples, but maybe you're familiar with this when I say I'm going to take for now a set of RD, and then I'm going to take some integer, and just as a very easy first definition, its K dilation is going to be just K times X for X in S, and then we're going to look at dilations all the time. So maybe the first definition is the Ehrhart counting function. So the Ehrhart counting function, maybe I should ask, is this like a size of handwriting fine? Yeah, okay. I think you can zoom anyways, right? Okay. Yeah, the Ehrhart counting function of this bounded set S of RD is just given by, I'm gonna denote it by air with a small e, because you'll see why. And then this is a function that will take an integer, non-negative integer, to another non-negative integer. And I'm going to take some k and map it into the number of points on the kth dilation of S, of lattice points. And this is very important. Yeah, so, okay. So to like really grasp this definition, let's do some examples. And here I'm going to throw out some questions. So very easy question. If I give you an interval, A to B on R, and then we assume that A and B are integers, and let's say non-negative just because it's easier, and I'm going to draw this, for example, like this, right? And this is my interval. And okay, question to you, how many lattice points does this have? 5, yes, this is great. But what if A and B are not 1 or 6 or any number specifically? 3, okay. Yeah, exactly. So if I write that in terms of A and B, this would be B minus A plus 1 lattice points. Do you agree? Yeah, okay. Also, there's some people I cannot see, so maybe if you have questions, you can just write. But how about the kth dilate? So the kth dilate, if I call this L, then this is B, the interval Ka to Kb. And how many lattice points does this have? Easy question now. Same thing, but with A and B. Okay. Yeah, I know online talks are hard. So we have KB minus KA plus 1 lattice points, right? Yeah. Okay. So then I'm going to leave this here. What is our Ehrhart counting function? So can you give me an explicit form of the Ehrhart counting function of this interval L that depends on K? Well, this is just what I've written, right? So this is K, and then I can factor this out, plus 1. Great. Okay, that was easy, right? But what is this, and why am I taking so much time with an interval? Well, this is a polynomial in degree of K, 1, right? Which weirdly coincides with our dimension of the interval, but we'll get to that later. Okay, and then let's do a second example just to make sure we're all on the same page. So what if I take the unit cube and I ask you the same question? So how many points? Wait, let me do this more general. I can take the cube in any dimension. So let's do this. The picture is just for reference because I can draw higher, but what is the Ehrhart counting function of this cube? Okay, so let's start with the kth dilet. Right, so the kth dilet is 0 to K to the D, right? So our Ehrhart counting function is, well, how many points do I have? If it's from 0 to 1, I have 2 times 2 times 2, right? But if I go higher and I take K, so this is K plus 1 to the D, right? Okay, and then again, I'm gonna write this here. This is a polynomial in degree of K equal to D, right? So far, so good. But what if I ask you to list all the lattice points on a given polytope? How would you do that? If I give you the interval from 0 to 5, then you'd say, oh, it's just 0, 1, 2, 3, 4, 5, right? But what if I take something like, okay, list all the integers from 0 to 1,000, then it gets harder, right? Because then you have to write 1,000 things down. And if I go higher in dimension, then it's harder and harder, and it's not feasible anymore, right? So this is where generating functions will come in. So let's talk about generating functions and we'll stick to lattice polytopes. And yeah, so what our idea is here is we want to encode points, or specifically lattice points, efficiently. And how would you do that? Well, our naive attempt doesn't work, right? If we list all of them, it's just not possible. So how about this idea? We can replace some, let's say, K in our polytope with a monomial. And I take some variable T to the K. Right? So if, for example, I give you this P3, it's just the interval from 0 to 3, then, well, 0, 1, 2, 3. Oh, yeah, there we go. So how would you write it in terms of this idea? Well, T to the 0 is just 1, right? So I get 1 plus T plus t squared plus t cubed. Right? So far, so good. Okay, I see some nodding, that's great. And this is what I'm gonna call a lattice point transformation. Which is basically just going from lattice points in polytopes to monomials. Right? And so if I want to write this in a more compact way, well, this is just the sum from I equals 0 to 3 of t to the k, which I can write as let's say rational function, right? Because I can use a series expression, let's say. And this will come in handy later because this is basically the main idea behind Ehrhart polynomials, H-star polynomials, all that kind of thing, if you've heard about it. So let's try and generalize this for cones. So far, some questions. Are there anything you want to ask? No, it's fine.
I have a quick question. So your idea, you said replace K in element of P. So in this case, K is not the dilation factor.
Yeah, no, the notation, yeah, you're right.
Okay.
It's just the lattice point, yeah.
Right.
Yeah, I shouldn't have called it K. Yeah, but you're right. This is not a dilation factor, this is just like an element on P.
I guess I have a second question. If you're in multiple dimensions, which may be where you're headed already, do I just have a variable for each dimension?
Yeah, so for example, if you're higher, you would have t to the k, meaning something like t1 squared t2 cubed. And this will correspond to your lattice point 2, 3. Yeah, that's a great question. Thank you. Okay, so then we can talk about generalization to simplicial cones. And why I'm doing this, it's because this is how it was traditionally done by Ehrhart when he proposed Ehrhart theory a while ago. And so what we want to do now is, let me draw a cone. And so what we want to have here is, and I'm going to draw for this seminar a very nice cone. Well, because otherwise it's too hard, right? And then let's say we have such a cone. And then I extend this. And I want to count the lattice points on the cone. Right, so how would you do that? Do you have any idea? This is an infinite thing, right? So here the representation in monomials will come in handy. No idea. Okay, so a hint. Simplicial cones mean that they have linearly independent generators, right? So I could use this somehow. I could use the generator somehow. And the idea, or what we're aiming for, is I'm going to construct what's called a fundamental parallelepiped, which is basically I take, and maybe I can write it here, a fundamental parallel. Oh God, this is 2 L's, 1 P. Okay. Yeah. Okay. And this is basically I take all the generators of a cone, and I take the sums of this generator times some lambdas, and these lambdas are including 0, but strictly less than 1. For B in B, where B is just a set, A1 up to AD of primitive rate generators of the cone. And let's call this K. Okay, so in our example, K is just this cone, and maybe we can write it as lambda 1 times 1, 1, plus lambda 2 times minus 2, 3. And this is lambda 1, lambda 2, greater or equal to 0, right? And so could you tell me how to describe the lattice points on the fundamental parallelepiped? Well, how many are there? Well, maybe this picture is not helping, but maybe I can highlight them really. Better, right? Okay. So we have 5. That's great. And then, yeah, and then what do I do with the other points on the cone? So I have 5 for now, right? But our idea is that if we translate this fundamental parallelepiped by the right amounts, then we're going to cover all of the lattice points on the cone, right? So basically,
Sophia.
K, yeah.
Sorry, would 1, 1 not also be a lattice point? Maybe I'm saying it, but
That's a great question. But it's not, because I'm requiring that this is strictly less than 1.
okay, yes. But then, I guess, okay. Yes.
Yes. Yeah, and that's why I do this, because otherwise I would double count a lot of points on the boundary. Yeah. Yeah, so K, the cone is basically a disjoint union of, let's say, translates of the fundamental parallelepiped, and I'm going to write this more explicitly later. But what is its lattice point transformation then? What was the lattice point transformation? Well, we can start by writing the points on the fundamental parallelepiped as going over the sum over J and K, and I'm using K a lot, but hopefully it's not that confusing, of C to the M, or I'm going to call it maybe T to the M to just be consistent with the variables. Right, so this is for the fundamental parallelepiped, or maybe for the translates of the fundamental parallelepiped more precisely, right? Because I'm going to translate by J and K. And well, I can split this into a sum over J and a sum over K of something very long here in the exponent, but it's just basically I'm taking away that M I start with. And this I can write as, again, a rational function, just using geometric series. And this I can write as such, right? And what I'm doing is basically I'm separating this into 2 sums. The first sum over K will give me the exponents on this part here, and the first part with J will give me this exponents here, 1 and 1. Okay, and well, the points on the fundamental parallelepiped are actually, well, I can write this very quickly. 1, 0, 0, 2, minus 1, 2, and minus 1, 3. Okay. So basically it's lattice point transformation, and when I take into account all of the points on the cone, will give me something like, on the top part, I will have a contribution from the fundamental parallelepiped, and basically I'm transforming all of this into monomials. So I have C1 minus 1, C2 cube, and then this horrible line. Yeah, and then I get the same contribution here as before. Okay, and why am I going to such trouble with writing C1 and C2? Well, because I want you to know. Oh, is there a question? No? It's
Sorry, I clicked on the wrong thing. Isn't it,
Yeah.
isn't the integer point 0, 1, not 1, 0?
0, 1. You might be right. Yes. 0, 1. Yes, yes, yes. Yep. Thank you. 0, 2. Okay. Yeah. And then I hope I did this correctly. And it's probably at C2 here. Yeah. Thank you. Questions? No, we're good. Okay. And this comes from the fundamental parallelepiped, and this comes from the generators. And well, this is nice, right? Because we've managed to express an infinite amount of points as, let's say, a very simple function, right? That gives us a lot of information about the cone. But the good thing about this, and here comes Ehrhart, is wait, let me write this as a theorem. And the theorem tells us that the Ehrhart counting function which sends k into Ehrhart p of k, and this is for k, let's say 0, extends, and this is this will come in handy in the Ehrhart theory. This extends to a polynomial function. And let me write it with a variable now of degree d, which is the dimension of p. And this was a huge theorem, right? Because it's not obvious that you can actually do this. It actually requires a proof, which is not hard, but it takes some calculation. But this was, let's say, a breakthrough. And what this polynomial is, it's called, and maybe you have heard about that, this is the Ehrhart polynomial of P. And here I'm now talking about polytopes, or more specifically, lattice polytopes. And this has been generalized to also rational polytopes, but let's not go into that case because it's a bit more complicated. But what we can define here as well is, if you noticed here, we start at some point talking about series, right? Because we have infinite things, but we can then define the Ehrhart series. And so now I'm going to take a lattice polytope. And so the Ehrhart series of the lattice polytope P is, and here I use big E, which is a bit confusing to be honest, but it's how it's done on most books. And this is 1 plus the sum. And here I'm going to count the points in the dilation of P and multiply this by t to the k. So basically what I'm doing is I'm taking a series, and then this one here, I could also write inside the series, right? Because t to the 0, we've established this one, and it all works out. But this can be written as also a rational function if we follow the same procedure as before, where the polynomial in the numerator has some coefficients which are called h0 star up to hd star, and then I divide by 1 minus t to the d plus 1, and this is what it's called the h star polynomial. So maybe, is this familiar at all? Was the h star polynomial before in your mind? Not really? Kind of? Okay, well, now we've seen it together. And the great thing is that this is very, very interesting, because from the H-star polynomial, you can know certain things about the polytope you started with, but not all of them. And a lot of these questions are still open, but maybe I can tell you some results. And for example, Stanley's theorem, and I am 90% sure that this was in 1980s, tells us that the coefficients of the H-star polynomial of an arbitrary lattice polytope are non-negative, right? And then if you're a combinatorialist, you hear something is non-negative and it's an integer, and then you start thinking about what this counts, right? So this counts something. And that's great because it actually does, but I'm not going to go into the details about what it counts. Maybe I can like mention it quickly. If you like order your polytope, let's say in an ascending way by some hyperplane given by the last coordinate, then you can give this like an acyclic orientation, and this each coefficient will count the number of points towards which another point is pointing. But let's just not go in there. That's like a very nice way to see it. But then people have been asking if there are other descriptions, and there are lots of open questions about the H-star polynomial also, if the coefficients are palindromic, if their coefficients are log concave, or they satisfy any more properties. And these are still open questions, but maybe I can do a remark before we move on to weighted Ehrhart theory. And the very nice thing is that the leading coefficient of the Ehrhart polynomial actually equals the normalized volume of P. And the second coefficient of this Ehrhart polynomial is 1/2 times the normalized surface area of the boundary of P. Okay, questions so far?
Yeah, I have a question. Is this H-star polynomial related to like the H vector of a polytope?
It is so you can for a polytope you can compute the H vector in terms of its F vector, but it's not the same. No, no. These are two different descriptions you can get from a polytope, and this will tell you different information about it, but I don't think they're actually related. I'm not sure why they chose such a close notation, but as we've seen, K is used everywhere, small and big E, so not great notation. Yeah.
Cool, thanks.
More questions? Any more questions, comments before we move on to weighted Ehrhart theory?
What does normalized mean? Sorry.
Yeah, so normalized means you take the Euclidean volume as you would compute it in a normal Euclidean space, and you divide by d factorial, where d is the dimension of this space.
Thank you.
Yeah, you're welcome. Yeah, this is counting basically tiny boxes on your lattice. But this is very interesting, because if we already have a description of the coefficients of the Ehrhart polynomial, and so we can compute at least two of them, right? For the other ones, we are not sure. Also, maybe I can tell you that the zeroth coefficient is always 1. And this has to do with the fact that if you evaluate t to 0, then the 0-dimensional polytope will have 1 lattice point. But yeah, that's just how we look at it. But so, okay, maybe just a brief overview of what is to come. So Ehrhart theory has a lot of discussion. There's a lot of experts in this field working here. They have lots of open questions. And so Jesus de Loera and other people were thinking, how about if we generalize this? And so here comes a weighted Ehrhart theory. And well, this is joint work with a lot of people. So Esme Bajo, Rob Davies, Jesus de Loera, Alexei Garber, Katarina Yuchemko, a lot of people working here, and Josephine Yu. And what we do here is now we're going to take polytope. And so we're going to take a polytope and RD. Hopefully a lattice polytope, but my drawing is not so good. And we're going to take W, which is a polynomial function. An R to the D of, let's say, degree M. And so if before we counted lattice points, now we're going to count the evaluation of these weights on the lattice points. And this is why it's called weighted. And so the motivation actually came from a computational problem. And so people wanted to estimate computationally this sum that depends on the polytope and on the weight. And basically it was just taking all lattice points on the polytope and computing the weight on that lattice point and just adding them all. And so this was a hard problem, but this is precisely why weighted Ehrhart theory comes into the picture. And so maybe I can ask you a very easy question. So how can we recover Ehrhart theory from weighted Ehrhart theory? Exactly, so that one. So exactly, so maybe similarity with Ehrhart theory. And so basically we recover Ehrhart theory for the case when the weight is just a 1. Right? And so also if we dilate the polytope P by some K, and K is now again my dilation factor. And so we get that this S PW, and then I'm gonna write that it depends on K is just a sum from M equals 0 to D plus M of some AM times K to the M. So basically the notation changed here, but this is basically, and let me write it as like the Ehrhart weighted counting function that we had before, right? Because what we're gonna do is we're gonna try and write it as a sum. And then I told you before that this was a polynomial in the dimension of the polytope, right? For the Ehrhart theory. But now it's a polynomial in the dimension of degree, dimension plus degree of the polynomial weight. So now we had a weight of degree M, and now we have M here as well. And so our weighted Ehrhart counting function is the polynomial of degree D plus M, which is very nice. Actually, this is not trivial at all. It requires proof. But that's a very nice result. And this told us, hey, we're going in the right direction, because if we take a polynomial of degree 0, then we recover, again, degree D. Questions? Oh, good. Okay.
Sorry, Sophia. What is AM here? Shouldn't I feel like we should
Yeah,
have
so
the
AM,
weight here?
let's just say these are coefficients.
Okay, great.
Which I didn't want to write down because in the case of rational polytopes, they're quasi-polynomials of period Q. For Q, the number you have to multiply, yeah, something. But
Okay,
these are just
great.
coefficients that you can write down. But the great thing here is that the first coefficient of this thing is actually equal to the integral of the weight over the polytope. Which, if you recall here, let me scroll a little bit further back up. So here I told you the leading coefficient of the Ehrhart polynomial was the normalized volume, right? And now I'm telling you, well, the leading coefficient here is the integral of the weight, which kind of makes sense because if we take again 1, then we're just getting the volume. Okay. And so this is great because people struggle to compute these integrals for a while, but now from the point of view of weighted Ehrhart theory, you just have to look at this lattice points on a polytope, and then this would give you the integral, which is very good. Okay, so yeah, so maybe a word of warning. The problem is harder now. Which doesn't mean less interesting, but already describing this coefficients AM was an NP-hard problem for normal Ehrhart theory. So you can imagine how it goes for more complicated ways. Yeah, so let me introduce you to a few notions in weighted Ehrhart theory. And so we have an analog. Maybe I can write this as a definition and call it the weighted Ehrhart series. And this is, and the notation will change a little bit here. And I'm gonna note that FPW of T, this series, which is basically the same as in the normal case, but instead we take the weighted Ehrhart counting function here. Okay. And so this is basically, and I'm gonna try and keep you up to the notation. This is the weighted version of the Ehrhart series that we had before. And I think I wrote it this way. Yeah, so the thing is that we can write this here again as some H star polynomial, but here we have weighted. And so on the bottom part, it gets a little bit more complicated, but we still can write this as a rational function. And here I'm gonna write some beta j's, which are, let's say, some exponents that will also come from complicated conditions, and which I didn't want to write down, but they will simplify to the d+1 for the Ehrhart theory case, and otherwise they have to do with the rationality of the polytope and so on. So let's just leave it at that. Okay, so our goal was basically to generalize Stanley's result. And so what was Stanley's result? Well, Stanley's result had to do with the non-negativity of the H star coefficients, right? So he was happy that we were counting something, and then we are happy if we count something also in the weighted Ehrhart theory case. And so for which series of weights do we get this non-negativity, right? Because it's not trivial, right? You start asking yourself these questions and you start computing things, and then you see that not all weights will give you positive H star coefficients. But maybe I can write a small spoiler here. We believe it works for W, a product of linear forms that are positive on P. And we're not saying then that this is an if and only if. We just looked at the product of linear forms positive on P, and well, this result holds. But maybe it's not the best we can get. We have a lot of open questions, but we can think about this as L, a set of linear forms. From R to the D to R. And so our question is, and I'm gonna introduce some notation here as well. When I write S of PL, I'm just saying I take all the lattice points on a polytope and then count its weights, which is a product of linear forms. Okay, so let's do some examples. And then you see how the examples here can get overly complicated very quickly. Right, so let's start with a cube, but I'm not gonna go to the dimensions just yet. So let's start with maybe a square. So let's take P to be 0, 1 squared. And let's take W instead of the trivial Ehrhart case, which is not trivial at all. Let's take X times Y. Right? So how would you go about counting the evaluation of this weight on the lattice points? Do you have any ideas? So what are the lattice points on P? Or the evaluation of the weights of the lattice points on P, maybe.
Would it be 1 on where X and Y are 1, 1, and then 0? So, okay.
Exactly. Yeah. No, this is great. So we can write this as like 0, 0 plus 1 plus 1, 0 plus 1, right? Kind of. We can go either this way or this way. Yeah. And so to be sure, let me just write 2 times P. Well, this is 0, 0 plus 1 plus 2, plus 1, 0 plus 1 plus 2. Plus 2, 0 plus 1 plus 2, right? So it already gives you a hint for KP. So this is basically the sum from J equals 0 to K of J times the sum from I equals 0 to K of I. Right? And this is, we can actually express this as a rational function, and the weighted Ehrhart counting function in terms of K is just K times K plus 1/2 times the same thing. Right? Are we good? Okay, maybe a second example. And again, I'm choosing the square. But let's take some weights, X to the M, Y to the L. Well, you can play the same game, right? And then your weighted Ehrhart counting function will be, you take here a product of 2 sums, And then you have j to the L. Yeah, well, it depends on how you write them, but let's say I to the M. Right, and these are Faulhaber functions. Faulhaber, let's say polynomials. And you can Google them and play with them, and they're very fun. But the thing is that already for the cube in a very, very easy, let's call it easy weight, we already have very nice combinatorics. Right, so this is very cool. But the reason I'm not doing more examples is because they're hard to compute. You don't have the symmetry for other things. We tried the simplex and it already gets not so easy to write, let's say. But our main theorem from the work we were doing was that if we take P d-dimensional rational polytope, in R to the D, an L collection of positive homogeneous linear forms, then the weighted H star polynomial for this weight, which is W, is the product of I, Li. This has non-negative coefficients. Okay, questions so far? Maybe let that sink in. So I want to talk about this assumptions we're doing because it seems quite strong, right? We're requiring our weights to be a product of positive homogeneous linear forms. But the thing is that we've had examples where if we drop one of these assumptions, well, it doesn't hold anymore. And so maybe I can talk about why we need, for example, homogeneous. This one's easy to see. Why homogeneous? Well, if we take already P equals 0, 1, what is the Ehrhart series of this? The normal Ehrhart series. So I can write this as P and then weight 1 of T, right? Do you have any idea what this might be? This is a very easy geometric series, right? And so basically if I skip the sum step, I get 1 minus T squared. Right, because I told you before it was over 1 minus T to the D plus 1. D is 1 in this case. So D plus 1 will be the square we have on our denominator. And what if I take, for example, I take the same polytope and then I take the weight x squared, right? So basically I kind of told you on the examples how to compute it. But not quite, right? We still have some work to do. So this is the sum, and maybe I can write it from K equals 0 or greater than 0 of this SPW of K times T to the K, right? And this I told you, it had to do with some Faulhaber polynomials, whatever that means. Right. But well, let me save you some computation time, this is actually t squared plus t over 1 minus t to the 4th power, right? Because we had our denominator to be of degree d plus the degree of the weight, and the weight is degree 2, or plus 1, d plus 1 plus the degree of the weight, and so it's 2 plus 1 plus the dimension of the polytope, right? So maybe I can write that down. This is d plus m plus 1. Okay, so from this, it should be, or kind of should, but it's not easy to compute this, right? So what if I take weight that's just the sum of both of those weights? Well, this one I'm not gonna make you compute, but this is already 2 times t squared minus t plus 1. And here I get 1 minus t to the 4th. So do you already see the problem on here? What is this I've just computed? This is the weighted H star polynomial, right? And so if it's not homogeneous, so this is not homogeneous, right? So then we already have a negative here. So not great. And this was a very, very easy example on just a 0-1 interval, right? Okay, so we've talked about the homogeneous hypothesis, and positive, I here mean each linear form has to be positive on the polytope. And then we have another result, which tells us that if the product of all of them is positive, then the evaluation at any positive point is positive. But this is not the same. This is not having H star positive coefficients. And this also requires some proof. But the proof of the main theorem, and I'm not gonna do it because I have like 5 minutes left, right? Yeah. So let's call this a proof of the main theorem. Is basically following Stanley's proof for the Ehrhart theory case. And basically he's just does the proof for simplices and then extends to polytopes by an argument of counting points on disjoint cones. So the way we did it before, so he took the polytope, took the cone over that polytope and separated that into simplicial cones. And the simplicial cones were disjoint, so he was not double counting. And the same way we did for the fundamental parallelepiped, he proves this in general. And this is how it worked for us too. But maybe just one last comment, and then we have like 2 or 3 minutes for questions is, so what about other questions? So do we have an analog for, so let's just maybe write this quickly, open questions. Do we have an analog for the second coefficient? For second coefficient of the weighted Ehrhart function, right? Because I told you before in the normal Ehrhart case that it was 1/2 of the normalized boundary area or something. Yeah, but this we don't have here. And we had it for the first one, which was the integral becomes the volume, which was really nice, but we still don't have that in this case. And so can we talk about other properties of the H star polynomial that hold in the weighted case? So for example, log concavity, real rootedness, also palindromicity. These are words you will hear very related to Ehrhart theory because people have been studying a lot of these properties. And so do they hold in the weighted version? And is there a general form or like more general, let's say, for which non-negativity of the H star holds? So there's a lot of open questions. I hope I kind of motivated people to look into Ehrhart theory and see that this is a nice generalization. And if you're interested to talk more about it, I'm always available. You can email me. And I hope that was understandable in some sense.
Great. Thank you so much, Sophia. Let's all thank our speaker.
Thank you.
This is great. Thank you. And anyone have questions you want to ask? Feel free to unmute yourself or put them in the chat.
Oh, I realized I wasn't looking at the chat.
Oh, it's all good. I have a question. I'll start us off. Could you draw what we mean by extend polytopes into cones? Is it like I have a polytope and I draw a cone?
Yeah. So for example, if you take the square, then what I mean is basically I embed this at a height 1.
Mm-hmm.
And then here my drawing skills will maybe help if they were good. But this is basically what I mean. So I take the cone over that polytope. Right. And this is very interesting because at height k of this cone, you actually have the kth dilation of the polytope.
Yeah.
Which means that counting the points on the cone is the same as counting the points on each dilation.
Great. And then making this simplicial would mean just like splitting this up into like
exactly. So
triangles.
For this case in particular, we can like split this way or this way.
Yeah. Great. Okay.
Yeah.
And in the chat, thank you. That makes a lot of sense. Okay. In the chat, Leo asks if you've studied some cases of log concavity or real rootedness for this.
We really wanted to, but we haven't gotten to that yet. So this is still an open question. You're very welcome to study it as well. Yeah, but log concavity seems maybe easier, maybe not, but maybe easier than the other one. And yeah, so we've studied only positivity for now, but our plan is to like keep on asking these questions and maybe, yeah, palindromicity to start with would be better and then go higher. Yeah.
Great. If no more questions for now, maybe I'll stop the recording and we'll start the after hours of GOCC. Thanks so much again.
Guys.